So this is a talk about type systems and a lot of like interesting and useful things you can do with type systems. But in order to like understand what's going on in this talk, you should know what mathematical proofs are. Now, that's not a problem because all of you have taken CS70. How do I know that? Well, here's a proof, okay? In order to be a UP member, you must be a CS major, right? Next, in order to be a CS major, you must have taken CS70, right? Therefore, I can guarantee that every UP member must have taken CS70. Okay, so that's my proof, right? So hopefully all of you agree. So like, hopefully you all agree with this proof. Like, if there's an error, then just tell me, right? Um, so now let's look at a particularly interesting program, right? So this is Python, and this will actually run if you add like data class decorators over like the classes. So first, in order to have a class UP member, what I basically need is I need to provide one field called CS major, and this field needs to be of type CS major. Okay, that's what the syntax means. Okay? Now, what's a CS major? Well, a CS major is a class which contains a member which has taken CS70. Okay? And this member is of type has taken CS70. Now, what's a has taken CS70? Well, it's just something with a student ID, right? And a student ID is an integer. So now, so these are basically like introduction rules. These are basically specifying how can I get a person who's a UP member. So if I want to create a person who's a UP member, I need someone who's a CS major. And then if I need a person who's a CS major, I need someone who has taken CS70. And I can always get someone who has taken CS70 because I already know that I have integers, right? I can just give integer student IDs to people. So now I want to prove that if you give me a UP member, then I can give you someone who has taken CS70. So how do I do that? Well, first what I do is I take my UP member and I extract the CS major out of them, okay? And then I pass that to the function CS major to CS70. Now, what does this function do? Well, this function takes in a person who's a CS major, and it extracts the evidence that they've taken CS70, right? And so it returns a token of type has taken CS70. And that's what this function returns, right? So what did I do just here, right? So I know that whenever I create a UP member, I need to provide evidence or basically an object of type CS major, which proves that that person is a CS major, right? And then I can later on extract that information back and give it to you. So that's exactly what I'm doing. Now, this is a function definition in Python, right? And you can see that over here, this function takes one argument of type UP member, and it returns an object of type has taken CS70. And so this is kind of like an implication, right? That whenever you give me a UP member, I give you someone who has taken CS70. Okay, so just keep that in mind, right? And just to prove that this is a program and like this is a valid program, right? I could write something like, I can create J, and J is a UP member because he's a CS major, because he has taken CS70, and he has some student ID number, right? This is probably not his student ID number, but And so how did I create a UP member? Well, first I created a CS major. And in order to create a CS major, I created a person who has taken CS70, right? And that's how I got J. And then now But once I have J, who's a UP member, I can extract the portion of J which has taken CS70. How do I do that? Well, I apply my function UP to CS70 on J, and I get the portion of J which has taken CS70. So you can see that, I had a function which takes in a UP member and produces a person who's taken CS70, and I have a person who's taken CS70. So now I have a person who has taken CS70, right? So it's kind of like modus ponens. And we'll get to that like right next. And you should note that all the code type checks. If you run this through a type checker like MyPy, then you won't get any type errors. And so this basically proves that, if I have a non-empty set of UP members, which in this case is my audience right here, then I also have a non-empty set of students who have taken CS70. Because I can populate this set of students who've taken CS70 by taking the UP members and passing them through this function. Okay. So what did we just do right here? So there's something called the Curry-Howard isomorphism, right? Which says that propositions are the same thing as types. So a proposition like there is a UP member is a type UP member. And every proof is isomorphic to a program. In fact, like what we mean by a program right here is really just a function. And we saw that, I gave you a proof of, I gave you the proof that if I have a UP member, I also have a person who's taken CS70, right? This is just a proof using mathematical logic, right? And I directly translated that into a program, specifically these two functions right here, right? And I could technically just inline this function right here by doing upmember.csmajor.taken CS70, right? So really, I just have a single function over here. And this function is proving that a UP member implies has taken CS70, right? So like that's like the first demo of Curry-Howard isomorphism. And it's pretty interesting. So what this basically says is that whenever I want to prove a proposition, what I need to do is, well, first I convert my proposition into a type. And then in order to prove that my proposition is true, I need to provide evidence for it. And the Curry-Howard isomorphism really connects computer programming with something known as constructionist or intuitionistic logic. And in intuitionistic logic, you always need to produce evidence for your proposition. And so how do you produce evidence of a type? Well, technically evidence of a type being inhabited. Well, a type is inhabited if you can produce a member of that type. So if I can produce, well, I just showed you here that I can produce a UP member, right? That is enough to prove that this type is inhabited, right? And I relied on the fact that I have integers, because I have integers means I have people who have taken CS70, means I have CS majors, and means I have UP members, right? And so that's what we mean in the Curry-Howard isomorphism. Basically, when we want to prove a proposition, we converted it to a type, and we show that that type has a member. And common constructs in logic have their equivalent counterparts in various programming languages. For example, so the first thing is true. So what is true? Well, true is something which is always true. So you should always be able to produce evidence for true, right? And so different programming languages have different representations for it. Python calls it none, because you don't need anything to create none, right? You can just go open a Python interpreter and type none, and you get an instance of none, right? So it's a type which always exists, and it always has only one member, right? There's only one member of none type in Python, which is none. Similarly, in Rust, Scala, and Haskell, it's called unit, and sometimes represented by an empty tuple. Because again, you can just create an empty tuple. You don't need any other type to create an empty tuple. Now, the logical false is a little more mind-bending in programming languages. So please feel free to ask any questions about it, like if it's not clear. But basically, false is something that you can never produce any evidence for, right? I mean, think about it. If you produced evidence for false, then it would not be false anymore, right? The only reason it's false is that you don't have any evidence for it. So this type is actually not very well represented in programming languages. C++ somewhat uses void. I mean, it's a little bit hand-wavy to say that void is true and void is false, because void in C++ is really weird. But in languages like in Python, Python has a type called no return, and you can get it from the typing module. And basically, when you annotate a function with type no return, that means that function is never going to return. So what kinds of functions never return? Well, if you just have an infinite loop, that's never going to return. If you have a function like system exit, then that never returns, right? Because when you call system.exit, you don't return into the calling function, right? It just terminates your program and opens up the shell again, right? And in Haskell, it's called a bottom type because that's what mathematicians call it. And then Scala calls it nothing, and Rust calls it never. And it's also denoted by this exclamation point. And we're shortly going to see more examples of this. And then we have a couple more logical constructs. So when we want to say, when we want to prove a logical conjunction, right? When we want to prove that A and B is true, then we need evidence for A and we need evidence for B, right? We need both evidences. We need two pieces of evidence, right? And if you want to construct a tuple of type A, B, then you need an object of type A and you need an object of type B. So in that sense, tuples are basically equivalent to logical conjunction. And logical disjunction, again, is not something that programming languages are typically designed to handle. But Python has an amazing type system. So Python has something called a union. And in order to get, now in logic, right, when you want to have evidence of either A or B, then it's sufficient for you to give me evidence of either A or B, right? So if you want to construct an object of type union string int in Python, then it's okay for you to have a string, and it's also okay for you to have an int. And other languages have other representations for it. Now, I guess the most interesting part of this is what's an implication in logic? Well, a logical implication is a function definition in programming. Because think about what an implication says, right? An implication says that if I have some member of type A, if I have some evidence of type A being true, then I can produce evidence of proposition B being true, right? And in programming, well, if you have a function which takes in a string and outputs an int, and you give it a string, then it's going to output an integer, right? And so if you have evidence of the type string being inhabited, i.e. you can create a string, then you can pass that string into your function and get an integer out, thus proving that the set of integers is also inhabited. So that's why function definition is the same thing as a logical implication. And generics are basically used for universal quantification, because if you want to say for all propositions P, that for all predicates P, I guess, right, something holds, you similarly just, do a generic. And like if you've programmed with generics, then you know what I'm talking about. And if you don't, then you'll see what I'm talking about pretty soon. So Now, you might be thinking, well, where's negation over here? So negation is a little hairy just because dealing with no return and never is a little tricky in most programming languages. So remember that not P is equivalent to not P or false, right? But then this looks an awful lot like the definition of an implication, right? So not P or false is the same thing as P implies false. And now we know how to represent P implies false in code, right? We basically need a function. So callable is what the function typing module calls a function. We need a function which takes in an element of type P and produces an element of type no return. Okay. So this type, this is a type alias, right? This type is basically the type of the negation of a proposition P. And in Rust, you write it as type not P. And this is your first taste of generics. So you're probably familiar with generics in Java, and it's the same thing in Rust, right? So not of some type P is the function, is a function, is some function, which takes in a parameter of type P and returns the never type. Okay? And what this basically means is if you were to implement a function like this, well, you'll not be able to implement a function like this. That's the point. Because you can never create a member of type never, because the never type has no members. And that's why I just have type aliases written over here, and I actually don't have any code written over here, because I cannot write any code that produces no return, and I cannot write any code which produces the never type. Okay. And then we can prove things like the distributive law, which says, well, P or Q and R is the same thing as P and R or Q and R. So how do I do that in Python? Well, I have a function which takes in a union of P and Q, and it takes in an R, and it returns a union of tuples, right? It returns a union of a tuple of P and R and a tuple of Q and R. So this means that, well, if I can write a function body that matches this type signature, then I will be able to, then I'll have a valid proof, right? That'll basically, so if I can write a function body, that means that the function type is inhabited, right? So how do I write it? Well, I check if P or Q is an instance of P. If it is, then I can basically assert that P has type P, and I return a tuple P comma R. Otherwise, I know that P or Q has type Q, so I assign it to a new variable with type Q and return Q comma R. Okay. And in Rust, what I need to do is I need to define an enum either, PQ, and this enum has two variants, a left variant and a right variant. The left variant contains the type P, the right variant contains a type Q. And then I basically use pattern matching. So if P or Q has type left and it contains some P, then I return a left containing a tuple P comma R, which is of type P comma R, right? It's a tuple. And if I have a right Q, then I return a right containing a Q comma R. And so that's how I prove that this function signature is valid, that I can basically write a function which matches the signature, right? And so that's basically the proof of this proposition, right? And then, of course, function application is the most, I guess, basic thing, which is like, it's called modus ponens in Latin, I guess. That's what like the propositional logic people call it. So like, so that basically means I need to create a function apply, which takes in a function, right? P to Q is a function which takes in a P and returns a Q, and it takes in a P. And it simply applies P to Q to P and produces an instance of Q, right? And the same thing in Rust. You take in a function that goes from P to Q, you take a P, you apply that function, and you get a q, right? And this is basically saying that, if I have, so p to q, which is a function, the function p to q is a way to convert evidence for p into evidence of q. And I'm also saying that I have evidence of p. Well, that means I can just apply this function to this piece of evidence to get evidence of q, right? And you can show that this particular tautology, or this particular implication in propositional logic, is the same thing as currying. And you can just check that this is true. And then universal quantifications is given by generics. So, for example, if I want to show that p and q implies q and p for all p and q, then I need to write a generic function. So these are basically type parameters p and q. So this is saying for all types p and q, if I have a tuple of type p comma q, then I can return a tuple of type q comma p. And how do I do that? Well, I take p and q and extract its second element. And then I take p and q and extract its first element. And then I wrap them up in a tuple again and return that, right? And yeah. And these are just some more examples. And this is just the same distribute function from before. But now I'm saying that for all p, q, and r, my proposition holds, right? And so that's basically given by me just adding this particular portion, making it a generic function, right? And contraposition is also quite interesting, right? So first I create type aliases to help me write the function. So not p is a function which takes in p and returns no return. Not q is a function that takes in a q and returns no return. Now, contraposition is a function which takes in a function from p to q, that's that, and it outputs a function which takes in not p and gives me a not q, because again, that's what implication means, right? And I basically do that by constructing the contrapositive. The contrapositive is basically something that takes in a not q and produces an instance of not p. How do I do that? Well, I construct another inner function which takes in evidence of p. Now I have a function p to q right here, right, which takes in evidence for p and turns it into evidence for q. So I first apply that in order to get evidence for q. And then not q is a function which takes in evidence for q and turns it into basically a no return, right? Turns it into false. So I just pass in the evidence for q into the function not q, and I get my contrapositive. So that's how one would implement something like contraposition using a program, right? And also, p implies not p, right? And I can come up with an implementation of it like this. You can check it later on. Now, very interestingly, we can prove that p implies not p, but we cannot prove that not p implies p. And the reason for this is actually kind of subtle. So when I have not p, right, I only have functions like not p is a function that takes in evidence of not p and returns no return. But what is not p? Not p is a function that takes in evidence of p and returns no return. So I only have functions which return instances of no return, right? Or of bottom type. So I only have evidence for false. I don't have evidence for p. So I actually cannot just produce evidence for p out of nowhere. And so in intuitionistic logic, and likewise in programs, you cannot prove double negation elimination. And Haskell allows you to bring in language extensions, and if you want to implement full-on logic, then you basically need to hack your way through the language in order to get double negation elimination. And similarly, proof by contradiction is also not there, because proof by contradiction is equivalent to double negation elimination. And law of the excluded middle is also not there. You cannot prove that this is true because it is equivalent to double negation elimination. And I have a couple examples where like double negation elimination like it does not hold in topology, like actually where the law of excluded middle doesn't hold, but that's the same thing as double negation elimination, right? But in in the interest of time, I'm just going to skip over those. Okay, if we have time later on, we'll like go over it. So let's go over like why does all this matter? Like you literally would never be writing like proofs of propositions with like programs, right? Unless of course you're a mathematician, in which case, you know, type theory and type checkers is exactly the way that you check proofs. Like you may have heard that, you know, the proof of the four color theorem in graph theory was proved by a computer. Well, how was it done? Well, it was written in a language called Coq. And all the axioms and all the theorems were written as propositions. And then you had this computer program basically like check a bunch of like, I think a couple thousand different cases. And basically that was how people proved the four color theorem. But you're typically not going to be doing that. So why should you care, right? You should care because if you have a good type system, then you get a lot of guarantees before running the program. I mean, it's really great because you can think of it this way, right? We as a programmer are like someone who's writing a recipe, right? We write instructions for what the computer should do. Like, just like, you know, if you're writing a recipe, then you're writing instructions for how someone should cook, right? Now, some recipes you can like tell right away that they're bad, right? For example, if you want to cook some spaghetti, and one step in the recipe says add rat poison to my spaghetti, then you clearly know that that's bad, right? So you'll immediately reject that recipe. But, you know, you need a more sophisticated chef, right? You need a more intelligent, experienced chef to tell you that, well, okay, instead of adding like 100 grams of cheese, maybe you should add like 75 grams of cheese, and that'll make your spaghetti taste better. And so that basically, so if you had access to that good chef to verify your recipe, then you wouldn't have to like cook your spaghetti, taste it, and then realize it's bad, right? The chef would tell you automatically, right in the beginning, that your recipe is bad. And that's exactly what we can do if we have a good type checker with a good type system. We can basically let the type checker check whether our proofs are correct, whether our program is correct or not. And that way, we don't have to fail at runtime, right? And so we don't have to run our program in order to know that it's wrong, right? We know that it's wrong if it doesn't compile. So that's why it's good. Like, for example, if you have like isInstance, like if you've written Python code, then you've probably come across isInstance. And like if you're writing, you know, code without types, then you have to check, for instance, like you have to do these isInstance checks. Otherwise, your program is going to error, right? With types, if you have a good type checker, like say MyPy, you don't need this isInstance check because you won't be able to compile code that has, you know, incorrect type. So if you pass this function anything which is not a CS major, then this function will, then MyPy will tell you that there's an error and you should not run this Python code, right? And similarly, you might have a function which has a particular return type. You know, without type checking, you might be doing something like this. But sometimes none is none sometimes, so you cannot multiply, right? But you don't know that when you've just written the code, right? You need to run it a couple of times, and then you'll realize that, oh, wait, I didn't handle the case when sometimes none is none, right? Whereas with type checking, the type checker will force you to handle the case when sometimes none is none. So I have to include this if-else condition over here. Otherwise, my type checker is going to complain. And you know, I could also resolve it in some other ways and get something more monadic. I can talk about monads later. It's related to functional programming, if you've heard of that buzzword. And now that brings me to Rust. Okay, Rust is a great example of type systems being put to good use. because because Rust as a programming language provides a lot of guarantees about memory safety just at compile time. So you cannot dereference null pointers, you can't have data races, you can almost not have double freeze, and there are a lot more nice things that you can. There are a lot more like nice memory guarantees that you get with Rust, and it does all of that using a type system, and it does that by basically. So it has two concepts. So the first concept is ownership and borrowing, which I am going to cover in this talk, and the other concept is lifetimes, which you may have come across if you've studied C++. But I'm not going to go over lifetimes because it takes about like half an hour to explain lifetimes, right? And basically, the Rust borrowing system says that you can either have multiple immutable pointers to the same piece of memory. So R is like point A is basically an array in some part of memory, right? And I can basically create multiple pointers to that same array, or I can only have one mutable pointer to it, right? So this is how you create a mutable pointer. You just say reference mute, right? And so over here, I create a pointer 3, which is a mutable reference to array. That is okay. But then I take another reference to this pointer, and that is not okay. And this is because, when you have a pointer to a piece of memory, when I have a mutable pointer to a piece of memory, I can do anything to it, right? I can simply, for example, free that array. And then if I have more pointers to that piece of memory, then those become dangling pointers. And that can cause all sorts of memory issues, right? And it can also cause like security bugs. It often does in C++. So basically that's what Rust prevents. And it does that by tracking types. So pointer 1, pointer 2, and pointer 4, which are basically taken like this, they have type reference to array of 32-bit integers. Whereas pointer 3 and pointer 5 have type mutable reference to an array of I32s, 32-bit integers. Okay. And I'll be comparing this to C++ a lot because Rust is a low-level systems programming language just like C and C++, right? And basically the gist of it is that the Rust type system allows you to check for mutability, allows you to check for exclusive access at compile time. Whereas if you want to do the same thing in C++, you can use std unique or std shared pointer, but those are runtime reference counted. And so they add a runtime cost. Whereas in Rust, you don't get any runtime cost, but you get the same memory guarantees. What's more, your program is not going to crash at runtime because you basically created like an alias to a unique pointer, for example. And this is basically an example where I create a vector, then I take a pointer to that vector, then now I have two pointers, right? R is a pointer to this vector in memory, pointer is a pointer to this same vector in memory, and then I basically deallocate it, and then I try to access it again through pointer, and basically it's like false and does all sorts of weird stuff. And the point is that the equivalent Rust program does not compile because over here because pointer is an immutable reference to array. And in order to basically deallocate, in order to delete my array, I need to pass a mutable reference to the array. And that basically now violates the contract in the compiler, which says that you can only have one mutable reference at a time. And when you have a mutable reference, you cannot have any immutable references or any other mutable references, right? And this is basically the error that you get. So it says immutable borrow occurred here. And then you try to take a mutable reference, but you are also going to use the immutable borrow later. Now note that it would be okay if I never used this. If I never use pointer, then the compiler is actually smart enough to just optimize pointer away by line 4. So at line 4, the pointer is not live. And so this is fine. This type checks. Okay. And over here, I have another example of like how you can optimize a piece of Rust code, how the compiler can optimize a piece of Rust code. And you actually cannot do that with C++. And you also cannot do that with C++ if you add const. So const does not solve all of your problems in C++. Okay. But yeah, I'm just going to skip over that to, I guess, what's the coolest part of this talk, which is you can check the length of an array or the size of a matrix at compile time in Rust. So look at this Python code, right? I presume that most of you are familiar with NumPy, right? So A is a 2x3 matrix, and B is a 4x5 matrix, right? And I try to do A dot B, right? This Python code compiles. And when I say compiles, I really mean it compiles, because Python does have a compiler, and then it runs on an interpreter, right? So this code compiles, and it produces an error at runtime. But what if I tried to write the same code in Rust? It would look something like this. Okay? So let me just quickly unpack this type signature right here. So I'm saying A is a matrix. Okay. Now this matrix type is generic, and it's generic in the data type, which is in this case 32-bit floating point numbers. Then I have two interesting things, U2 and U3. And U2 and U3 over here are basically type level numbers which represent the size of the matrix. U2 is a type level number which represents 2 at the type level. And 3 is something that represents 3 at the type level. So it's a type, but it really has a meaning in terms of numbers. And matrix array is just the container type. And you see that it also has a data type and 2 more types which specify the shape. Now, what these are exactly, I'm going to get into just a second. But the point is that the Rust compiler knows the shape of A and the shape of B at compile time. Okay, that is huge, right? And this is basically how you call a static method on a class. So this is just a type signature, and I'm saying, take this type signature, right? Now this entire thing is a class, right? And now I'm calling a static method which creates the zero matrix of this shape, right? And so that's what this code means. So A is a zero matrix of shape 2x3, and B is a zero matrix of shape 4x5. Okay. So the Rust compiler knows the shapes of these matrices, and the compiler actually gives a shape mismatch error at compile time at this line. Because in the matrix dot product function, there is a constraint that says that this number over here must be the same as this number over here, which says the number of rows in one matrix must be the same as the number of columns in the other matrix, right? So what does that look like, right? So this is the type signature, and yeah, so it's basically a generic type, and these are type level numbers. And also, one important point about type level numbers is that they get optimized away at runtime, so you're not adding any runtime cost. So this is what the matrix multiplication function looks like. Now, Rust has operator overloading just like C++ and Python. And so you need to say impl, which means implement multiplication for this matrix. Okay. And there are a bunch of different type parameters because these are generic. But for our discussion, what's important is the row and column shapes. So what this is saying is I'm going to implement multiplication between a matrix of shape R2 by C2 and a matrix of shape R1 by C1 only when I have this constraint, this shape constraint called R multipliable is satisfied by R1, C1, R2, and C2. That's what this is saying. And just for a second, what proof is this producing? Well, this is producing a proof that I can multiply a matrix of shape R2 by C2 and R1 by C1 only when R1, C1, R2, and C2 are multipliable, right? And what's the implementation of R multipliable? Well, R multipliable basically says that, I can create an instance of this type when I know that C1 and R2 are equal. DimEq is basically a type which only has an implementation when C1 and R2 are equal. Because like right over here, I have the definition of DimEq. And DimEq is only defined when, so DimEq is only defined for shape constant, shape constraint, when I have the same D over here. So if C1 and R2 are not the same type, then there will be no implementation for shape constraint. So when the compiler is checking the types, what the compiler is going to try to do is the compiler is going to try to generate an instance of DimEq C1, R2 for shape constraint. But I've told the compiler that I can only produce that evidence if C1 and R2 are the same. So that's why the compiler can tell me that the proof you've written is incorrect if C1 and R2 are not the same. And only when C1 and R2 are the same, the compiler is able to produce an instance of shape constraint which matches DimEq D comma D, because C1 and R2 are the same thing, right? And yeah, just a side note is that you see that all of the bodies for these traits are empty. And that basically means these do nothing at runtime. These are just enforced at compile time, and they get completely optimized away at runtime, which I think is super cool. And now I'm basically going to end this with a demo where we basically implement part of this on our own. Okay. So I begin by implementing a trait called number. Okay. So what is number? Well, I technically don't even need to have a body over here. I can just have a trait number, but for debugging purposes, it's useful to have one single associated function, which basically returns the integer representation of that number. Okay. But these are all going to be type level numbers. So how do I create numbers? Well, so in Rust, a struct is basically the way to create an object. So if I were to write some Python code, then it would be something like class 0. And then I would write something like def to int, which takes in nothing and returns an int. And I do like something over here, right? So this is the same thing. So I define a struct called 0. And then what I do is I say that 0 is a number, okay? And this is a lot like interface implementations in Java. So if you've ever coded in Java, Java interfaces are basically equivalent to traits in Rust. And when I say implement number for 0, that means implement the trait, implement basically the interface number for 0. So how do you do that? Well, you just implement this function toInt, right? And how do you convert the type 0 into a number? Well, you just return 0. Okay. Next, we implement a struct called successor. Okay. Now, you should not care too much about what this is. That's just a type marker to make the Rust compiler happy. But yeah. This is basically the definition of a struct, another class. Now, this is a generic class. And what I'm saying here is the successor is generic in some number. So this n must be a number. So for example, I can do something like, type 1 is the successor of 0, for example. That's valid. And I need to implement number for I need to implement
There's a
number.
whole group of facts, so I don't really care if a class. What does that say?
Sorry, what was that? Okay. Um, so yeah. Um, so I'm implementing this. So now I say that, well, every successor is also a number, right? And one is just a type alias for sub of 0, right? And similarly, 2 is a type level number, which is the successor of 1. And just to convince you that these are, in fact, like what they seem to be, I can print out these numbers. So if I print 1 to int, let's see what I get, right? If I run it, it basically prints out 1 over here. And that basically shows that, well, yeah, this implementation is correct. And I can also print out, 2, like that. And now it prints 1 and 2, because guess what? When you convert the type 1 into an integer, you get 1. When you convert 2 into an integer, you get 2, right? And now I can implement things like the equal trait. So what does it mean? So now I have this trait called equal. Now, what does it mean for something to be equal? Well, I know that 0 is equal to 0, so I can implement equal 0 for 0. Okay? And this is just me making an assertion at the type level. So if at any point the compiler sees, 0, that a certain number needs to implement equal 0, then it knows that only when that number is 0, I'll find an implementation, right? And now I can implement equality for the rest of the natural numbers um, recursively, like this. So I say that the successor of n is equal to the successor of m only when m is a number and m is equal to n and n is also a number. Okay, so think about what this is saying. This is saying, well, this is asking, well, okay, how do I know that 3 is equal to 3? Well, I know that 3 is 1 plus 2, and I know that 2 is equal to 2. Well, how do I know 2 is equal to 2? Well, I know that 2 is, 1 plus 1. How do I know that? Okay, well, then now I have 1 and 1. How do I know 1 and 1 are equal? Well, 1 is 0 plus 1. And now, do I know that 0 is equal to 0? Well, yes, I know that 0 is equal to 0 because of this. And in fact, the type checker is actually going to unroll that entire recursion while type checking your program. Okay. And similarly, you can implement is greater than, and we know that the successor of any natural number is greater than 0. So we have that implementation. And then we know that the successor of n is greater than the successor of m if m is also greater than n, right? And we can also perform addition. And now when we perform addition, we basically take in an input number, we implement it for another number, and the output is over here. And well, I guess we're running out of time, so I may not be able to explain this entire code, but this code basically implements addition. So this says that, well, how do I add m plus 1 to n? Well, I add m to n, and then I add 1 to it. So if I want to add the successor of m to n, then I first add m to n, and then I add 1 to it. So what would I get if I were to say print 2 plus 3? So how would I print 2 plus 3? Well, I would say 2 as add 1, and I convert that to integer. I also extract output. info. I guess I need one more input right there. Okay. And now, if I basically run this code, well, what I'm doing is I'm doing 2 plus 1. And so this output should be 3, right? And so indeed, I get 1, 2, 3. So I was able to add type level numbers. And remember, this is just the compiler generating a type. This is not happening at runtime. This entire thing is being generated at compile time. And the compiler is basically inlining the value 3 over here, right? And finally, I can now implement a list, so I'm basically going to take the built-in Rust list type, which is a double-ended queue, and I'm going to add an extra annotation, which is the length of the list. Okay. So how is this useful? Well, first, I need to be able to create lists. So I can create an empty list using nil, and I can create, I can keep building lists recursively using cons like this. And if this reminds you of scheme, then well, that's exactly why I named these nil and cons, because they serve the same purpose as in scheme. And what nil does is nil produces a list of type t and 0. And then what cons does is cons takes in some value of type t and takes in the rest of the list. And now this list has type tn, and it returns a list of type t and the successor of n. So in this way, when we're constructing the list, we're actually encoding the length of the list in the process of constructing the list. Okay. And so I can, for example, write a function zip, which is again generic in the types of the lists and the lengths of the lists. And this is implemented only when the length of the left list is equal to the length of the right list. Okay. And that is pretty cool, right? And I have the entire thing implemented over here. So I'm just going to copy that over here like that. Cool. So this is basically a bunch of examples of type level numbers. And this is how I create lists. And so let's try to see what the type of A is, right? So intuitively, like I'm putting in integers, and this is of length 3. So the type of A should be a list of int and suck, suck, suck 0, right? Because I'm applying the successor function 3 times. And indeed, the compiler is able to figure out the type signature correctly. This list has type int32, which is the data type, and then suck, suck, suck 0, which is 3, right? And I never provided that type explicitly to the compiler, right? The compiler is figuring that out by itself. And now when I like cons it like this, I get, suck, 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 suck of 0, right? 5 successors. And hello is a list of type string, and 5. World is a list of type string and 5. Now, I know that I can only zip lists which are of the same length. So what happens if I try to zip A, which is a list of length 3, with hello, which is a list of length 5? Well, my IDE is telling me that I have mismatched types, but just to make sure, I can try to run this program. And indeed, I get an error, right? It's saying expected list of this type, but found list of this type, right? And so the point is that an incorrect program is not compiling, and the type checker is being able to prove that, right? And remember what the type checker is doing over here. It's trying to find evidence of a proof about the natural numbers. And that is huge. You can, in fact, use these piano numerals to prove things like, 5 is greater than 4, or that, 2 times 4 is equal to 8. You can use this type system to prove things like that. And that is what the compiler is doing, right? When I call this function zip on A and hello, the compiler is trying to prove that 5 is equal to 3 But the compiler is not able to do that. And that's why it's complaining, saying that it can't compile my code. Because 5 is not equal to 3, so it can't prove it, which is great. Whereas if I comment out this line and instead try to zip hello and world together, well, the compiler is first going to try to prove that 5 is equal to 5. And the compiler is going to succeed. So the compiler will print hello world. So let's comment out those lines. And what I should see here is you can see that I had lists hello and world. And now they're zipped together, right? So I had HW, EO, LR, LL, and OD. So the compiler actually created an implementation for this function, right? Because it was able to prove that 5 is equal to 5. And so that is why I think type systems are really cool. And since I have nowhere to go to, I can take any questions at this point, if that's okay with, I guess, Chase.